Okay, so thank you. So we have the pleasure to have with us Professor Stefano Maci. Stefano has been working on metamaterial technology. He's a professor, I mean, at the University of Siena, and he has been working on this technology, I mean, for a long time. I mean, before that this technology became RIS or attracted the attention of people in the wireless community, and he's working on many, I mean, applications, and he also has a startup company, I mean, which is actually developing this technology. So, Stefano, I don't want to steal time, I mean, to your presentation, so please go ahead.
Thank you very much. First of all, you see the big screen, right? Not the small one.
Yeah, I can see your slides. Yes. I can see your slides.
It's all right. So, okay, thank you very much. Let me simplify a little bit the terminology according to what Marco has presented a moment ago. Introducing this terminology, RIS of order n or RIS n. This make reference to a particular type of RIS that are in increasing level of difficulty to be implemented and to be designed. And in particular, the functionalities that can be integrated in the RIS can be counted through an index n, leading to the acronym RIS n, or RIS of order n, where n denote the number of functionalities of the RIS whose name is initialized always by R, and this is a particular case. So we can introduce reflecting intelligent surface, which is RIS1, reflective reconfigurable intelligent surface, which is RIS2, and this is mainly what is considered today by Marco in his presentation. And next, we have also receiving and redirecting reconfigurable intelligent surfaces, RIS3, receiving, regenerating, redirecting reconfigurable intelligent surface, RIS4. So this is just to simplify the notation and the terminology, but it's essentially what Marco has already discussed and what is under discussion in a standardization organization like ETSI and 3GPP. And in particular, we will introduce the use of metasurface technology for implementing this physical level of RIS-N. In particular, the RIS-1 are purely passive and static, and they are constituted by dense subwavelength patches printed on the electric surface. They are sometimes referred as a smart skin, as Marco mentioned before. And RIS-1 responds to the electromagnetic incident wave with a non-specular reflection, something that seems to violate one of the most basic and fundamental law in electromagnetism, which is the Snell law. But they are deployed in a strategic way for filling with the field zones of wireless environment that are not covered by the base transmission, by the BTS. And since their intrinsic nature of passive reflectors, they have zero power consumption. They can process electromagnetic signals directly at the speed of light and reduce the latency and complexity with respect to corresponding fully digital solutions. And the intelligence in this RIS-1 is supposed to be the design of the non-specular reflector or the force focusing system in the Fresnel zone, and to minimize the visual impact as well as the strategic statistic deployment that minimize the costs. RIS-1 get a lot of challenges, in particular, the large area to be covered, the non-invasive deployment, the problem of standardization, and in particular for the right band allocation, and the Fresnel zone optimization of the coverage, the cost-effective materials, and the manufacturing processes, repeatability, mass productions, and qualification. Together with that, we have some electromagnetic models that have to be improved in order to overcome the challenges, and in particular, ray tracing through RIS-1 in the Fresnel zone, generalized physical optics, beam tracing, optimization tools for statistical coverage, computational full-wave methods for the analysis and design, inverse scattering, and the metasurface design for maximizing the efficiency. These are all peculiar, significant points that are in the electromagnetic community, especially in the antennas and propagation community. However, all the things should be rise up in a joint effort between the RPS community of IEEE, antennas and propagation community, and as well as for the signal processing and communication communities. So this is the first time probably that the two scientists, the two community works together on the same objective. RIS2, reflecting reconfigurable intelligent surfaces. These are probably the most interesting one, the one that has been presented by Marco more extensively, and they are passive but able to be reconfigured after the deployment. They do not amplify nor introduce noise when reflecting or reshaping the incident wave, do not increase the latency, and they are inherently reciprocal. So it works in bidirection, in two directions, from the base station to the user and vice versa. The power consumption is around a couple of watts and is needed just for maintaining the biasing of the electronic elements. The electronic elements in a scheme that was presented by Marco in the first introduction. And the reconfigurability could happen through electronic components, but even through material. And in that case, there are several challenges that are additional with respect to the one of RIS1. So integration of the MTS with electronics and FPGA, digital precoding for redirection and near-field focusing, dispersivity, bandwidth control, losses, speed, ultra-low cost of the electronics, low power consumption, and harvesting. This harvesting is for power autonomies. The electromagnetic model to be improved, in addition for those for RIS1, are modeling of electronic components as integral part of boundary conditions for computational electromagnetics, multi-beam design, surface wave coupling optimization, electromagnetic modeling for phase change material, in case the structure has been used by a phase change material like vanadium dioxide or strontium barium titanate of liquid crystal, maybe. RIS3 is a little bit higher level of complexity. They are also called smart repeaters, and this is the one that has been discussed by Marco before. They can amplify and redirect the RF signal. So they amplify and redirect. There is an amplification inside, so they are a little bit more complex structure that can be realized even with other type of antenna, not only with metasurface, obviously, even if metasurface can guarantee more compactness of the antenna and low cost, especially. The specific challenges here are the coupling of the two antennas in a reduced space, maintaining a low noise amplification at low cost, providing countermeasures for spurious oscillations, cancelling feedback at reduced costs, and realization of uplink and downlink switches with a high level of isolation. This is the main, probably this last is the most important thing in this type of thing. For the rest, they are transmitting and receiving antenna coupled together, and the metasurface can provide a nice technology to do it. The RIS4 is the one that was referred Marco to as integrated sets and backhaul, and can be seen as a regenerative version of RIS3, even if not necessarily fully bidirectional. They receive, regenerate, and redirect the signal. They can be seen as a micro base station with less power, interconnected to the macro base station and with access to the core network, and other type of peculiarity that are, let us see, can be integrated in metasurfaces. The challenges is the cost and power consumption, sharing different aperture or even the same aperture antenna over the same functionality in transmission and reception. The fourth type of RIS can be also integrated in the same heterogeneous smart environment. For increasing N, they have less and less green attitude. It means the RIS1 0 watt, RIS2 2 watt, RIS3 20 watt, RIS4 200 watts. And they are increasing cost, power consumption, and environmental impact. And for increasing N, indeed, it is decreasing the level of the simplification deployment and also the standardization requirement. All RIS type, as I mentioned, are compatible with the Metasurface technology. Let me say some words about it if I have time. Please, Marco, stop me if it is too late. The Metasurface technology started in 2000, and the first generation was essentially uniform in space and time. The second generation, the Metasurface started to be modulated in space. In the third generation, that we are the one that we are facing today, they becomes intelligent, tunable, can scan, can be digitalized, can be programmable, and can also operate directly at the physical level some operation that becomes a sort of software-defined aperture, software-defined boundary conditions. There is a main issue today that we should face. And all this type of new technologies have been reviewed in a recent Antennas and Propagation magazine, a special issue edited by Tony Gerbich and myself. It happened in August 2022. It's very recent. You can find a lot of this concept inside. All of them are very well suited for RIS. And maybe that we can even divide the Metasurface in three types. First one is lenses, the other one is anomalous reflectors, and the one is surface wave control. So transformation from surface wave to radiated wave directly from the surface. This is one example of it, in which you excite the surface wave, the elements are small, exhibit some degrees of freedom in order to depict the picture. They are very small in terms of the wavelength. The periodicity matches the periodicity of the surface wave, and this creates a radiated beam broadside. Same thing, if you change the holography of the surface, you can redirect the beam in different sense, in different way. And if you do it electronically, or you can do it with the material, you can get with a low-cost scanning antenna, and with a technology which is much more convenient with respect to the one of patch antenna, which is very classical. So, in conclusion, for increasing N, RIS N requires an increasing level of signal processing time, complexity, power consumption, environmental impact, electronic components integration, and costs. On the other hand, decreasing N requires an increasing complexity in the standardization processes, and these are under discussion in ETSI and 3GPP. And then Metasurface can create a very interesting low-cost technology platform for accomplishing most of the technological and electromagnetic challenging required by a smart radio environment. And dedicated electromagnetic model is still required for the automatization of the computational design and for the planning of the deployment. So with this, I would like to stop and thank you, Marco, very much for inviting me, and to the IEEE proceeding for having organized this webinar. Very useful. Thank you very much.